For my embedded systems project, I decided to solve a problem, make a simple product within my limitations that will have a positive impact on our social, environmental, and economic standard of living. To do this, I decided to make a product generally related to the agriculture industry, on a much smaller scale to ensure my plan was within my limitations on time and resources. My project is an indoor plant care system. My initial draft for this project made use of the LPC802's microcontroller alongside the moisture sensor, 3 photoresistors for data acquisition from the outside world, namely the amount of water in the soil and the soil intensity and the sunlight intensity around the plants. I then included a 5-volt DC pump and an LED grow light strip for the system's reaction to the acquired data. And due to part limitations, the LED grow light strip was controlled via a set timer from my microcontroller instead of data acquired from the photoresistors. Each of my components used operates on basic building blocks of electricity and Ohm's law. The microcontroller is essentially a chip with integrated circuits within, controlling the decisions made by the entire system. The soil moisture sensor works using the principle of water resistance to electricity. In other words, the more water content in the soil, the lower the resistance is seen between the sensor's conducting plates, and the less water content in the soil, the higher the resistance between the sensor's conducting plates. The DC water pump is driven by a small electric motor that powers an impeller through a simple gearing system. As the impeller is powered, the pump either drives water in or out of the system. The grow lights are simply semiconductive light sources that emit lights when sufficient current passes through them. Electrons in the semiconductor recombine with electron holes, releasing energy in form of photons, which simulates sunlight to the plants. Now here I have all the listed components connected for a testing phase before assembly is completed for actual use of the product. Here are my LPC802 board. I'm making use of GPIO 8 and GPIO 12. GPIO 8 is set up to ADC5 using the FRO clock with a 750 kHz frequency and extracting digital values from the C register. The microcontroller reaches data from GPIO 8 and compares it against a set threshold. If the acquired data is below set values, the microcontroller changes GPIO 12 to output 3.3 volts, triggering the relay and powering our pump. During this stage, the moisture content is continually changing, and GPIO 12 will remain on until GPIO 8 reads a value greater than or equals to the set mean. The pump will turn off and the system will return to its default state when this condition is met. The pump is a submersible type. It needs to be completely immersed in water during operation to avoid burning the sealed-in motor. The pump's ground is connected directly to the 6V battery pack, and the power line is switched on and off with the relay as is good electrical practices. The LPC802 board powers the modules for both the moisture sensor and the relay using VCC and ground to provide 5V DC current. The LED strips for the purpose of this demonstration are connected directly to the 5V power line. All components connected to the board draw relatively low current and are well within the board's limitations. In this setup, the controller will see soil moisture levels way below the set value, and the feedback controller turns on the pump to reach the set mean value. As seen here, the system has been completely set up with a test plant, and all components have been securely mounted in a waterproof black pouch. We can now observe our feedback control system in normal operation. The system provides a controlled and reliable water supply for indoor plants. With proper use, it will reduce wasted water while improving our green ecosystem. It runs efficiently on very low power. The plant used in the demonstration requires the pump to turn on just once a day for a period of about 35 seconds. Aside its environmental economic impacts, the system has social benefits from its ease of operation to its sheer convenience and peace of mind when taking care of indoor plants.